There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, and protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and solarium, and bismuth, lithium, beryllium, and barium. Isn't that interesting? I hope you're all paying attention. There's going to be a short quiz later on. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercury and molybdenum and magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
Okay, Chemical Charlie here. I've got a liquid crystal display here, and I'm going to put my hot hand on it. Leave it on there for a few seconds. And then take it off, and you can see an image of my hand. Isn't that cool? And watch this. Now, the way that works is that the liquid crystal has a certain diameter or a certain thickness, and when you heat it up, it gets thicker, and the light waves interfere with one another, and you get a different color. So it goes from green to blue because different wavelengths are interfering with one another. So if you change the temperature, the thickness changes. All right, so I'm going to put this hot gun on to show you. Okay. And you can see it change color. And then as it cools, it will come back. It's more blue now. It was green.
But what exactly is liquid crystal?
Well, they're molecules, usually long chain molecules that line up in a certain pattern. All right, you can see it's coming back. I'm cooling it. They form an array, and the temperature determines how thick they are. So the thicker they are, the longer wavelengths would undergo constructive interference.
So do you know why it's called liquid crystal?
Well, they're not in a perfect order. All right, a crystal would have perfect order. So these don't have perfect order.
A crystal is a solid, right?
Yeah, these are not solid exactly. You know, they're semi-solid maybe.
They're semi-solid. They're in between a liquid and a solid.
You can see it makes the pattern of my hand, which is blue, and the rest is green.
They're in between a liquid and a solid.
That's right. So now I can erase this. You don't want to get it too hot because you could destroy it. And then if I cool it again, it takes a while to cool it. All right,
How would you destroy it?
Well, you could make it so hot that you kind of destroy the crystal. You decompose the liquid crystal into some other things that are not really a crystal. So that's what a liquid crystal is, and you could use it. You could have liquid different temperatures. I used to have. I left it where I used to work. I used to have a nice little thing that you could measure the temperature with using a liquid crystal. It would be a display, and the particular temperature would light up. There are mood rings that use this liquid crystal display, that kind of thing. I don't think it's quite cool yet, so it doesn't show up real well. Okay, so that's about all I have to say. Thank you.
It also has something to do with mood rings.